Hey everyone, welcome back. In this video, we'll be discussing about the third and the fourth problem of today's weekly contest. Count substrings that can be rearranged to contain a string, part 1, and count substring that can be rearranged to form a string, part 2. Both the problems are exactly similar, the only difference lies in the constraint and the memory limits of the problem. So we'll start from the very brute force way and try to optimize this step by step to fit in the time and memory limits of the last problem. So let's get started. The problem states that you're given two strings, words1 and word2. A string x is called valid if x can be rearranged to have word2 as a prefix. Your task is to return the total number of valid substrings of word1. So let's take an example. Let's say word1 is BCCA and word2 is ABC. So your task is to figure out how many substrings of BCCA are there such that if you rearrange the characters in the substring in any way you want, you would get ABC as the prefix of that rearranged substring. So obviously, if you want this to be the prefix, the substring should be greater than equals to 3, right? So there are only 3 substrings which have length greater than equals to 3: BCC, CCA, and BCCA. So let's figure out one by one whether each of these is valid or not. Let's start with BCC. Is this a valid substring? Answer is no, because no matter how you rearrange, you will not be able to form a string that has ABC as the prefix. Why? Because there is no A at all, right? Similarly, the second substring is also not valid because no matter what you do, you will not be able to arrange it in a string containing ABC as the prefix because there is no B in the current substring CCA at all. Finally, BCCA, this is a valid one. Why? Because you can rearrange it to form a string ABCC which has ABC as the prefix. So overall, you found just one valid substring and hence the answer here is 1. So hope the problem statement is clear. Now, what's the very brute force way to approach this? The very brute force way could be just simulate whatever is given. You are asked to find out the total number of valid substrings. You simply say, I will try out every possible substring, and if it is a valid one, I will increment my answer, otherwise I will not. So you can try out every possible substring starting at L and ending at R. So you'll start with this and you'll try to find out every possible substring starting at here and ending at different characters. Now for each of the substring, what you will do, you will figure out whether this is valid or not. So how to find whether a substring is valid or not is the question. So what is the definition of valid substring? You should be able to rearrange this such that you will get BB as the prefix of the rearranged string, right? Now, because you are free to rearrange, the only constraint that should be satisfied here is, do we have enough characters? If yes, I know I can rearrange in some format so that I can have word2 as the prefix, right? In this scenario, we have 3 A's and 1 B. What we need is 0 A and 2 B. So number of A is sufficient, that's fine, but number of B is not sufficient. What that means is, no matter what you do, you will not be able to rearrange this ABA into a string that has BB as the prefix. So this particular string will not be a valid one and you will not increment your counter. Whereas let's say you are trying out other substring, for example this one. In that case, again you'll do the same thing. How many A's are there? 2. How many B's are there? 3. Now you have enough A and you have enough B as well. So basically that means you can rearrange, you have enough characters to form word2, so you can simply rearrange the characters such that the characters appears in word2 occurs in the first and the rest of the characters appears afterwards. So this is a valid substring and you will increment your answer for this, right? So what is the pseudocode? The pseudocode for this would simply look something like this. You will try out every possible substring, which is you will start with every possible starting and every possible ending of a string, of a substring. Now, for every possible substring, you will count the number of characters that are there, right? And you will compare whether you have enough characters for each of those or not. For whether you have enough characters for each of the possible characters or not. If you have enough characters, you will increment your answer by 1. Forget about n minus r, that's not correct. So if it is if you have enough characters, you will simply increment your answer by 1. Now, what's the overall time complexity? You have 2 nested loop, so that will simply take order n square time, right? And inside those loops, what you're doing, you are first counting the number of characters between L and R. That count will require you to iterate over every character between L and R if you implement it naively. So that will take order and time in worst case, right? And what else? You are also then iterating over every possible character to figure out whether the count of those characters are sufficient or not. So that's denoted by C, where C is the number of unique characters that you can have. So you are iterating over all those as well. So this is your overall time complexity of the naive algorithm. Now, this n you can easily remove. How? You don't need to iterate over everything between L and R every time, because once you have the frequency of every character in this range, when you go to the next substring, you are just having one extra character. So instead of counting everything starting from L to R, you can simply increment the counter for B, and that will help you get what is the total number of characters between L and R for each of the characters, right? So this you can simply replace by a simple plus plus operation on the current character. So overall complexity would not have n, and the complexity would be n square c, right? Now this is your brute force complexity, and obviously this will not pass because the value of n is 10 power 5. So this is very huge. We need to optimize this. Now, if we need to optimize this, we need to remove one of these n for sure, because we can't afford 2 n's here. Where from these 2 n's coming from? Because you are trying out every possible substring. So you are trying out every possible L, and for each possible L, you are trying out every possible R. So if you need to remove one of these n, basically you need to remove one of these loop, right? Removing either L or R are almost equal. Basically, it means that you are iterating over every ending position, but somehow you are figuring out how many starting positions are valid if you remove L. But if you remove R, it's almost similar. You are trying out every possible starting position, and for each starting position, you are trying to figure out how many ending positions are valid without actually iterating over them. So what is the best way to remove this R? I would encourage you to pause and try to think for a moment. Notice that this function that we are trying to compute here is a step function. That basically means if you figure out that, okay, this is a valid substring, let's assume, then the next one will surely be a valid substring, and the one after that will also be a valid substring. Why? Because the definition of valid basically says, do you have enough characters to form every character at words 2? If yes, you are valid. Now, if you are saying that this is a valid substring, it means you have enough characters within these characters to form everything that's word 2 need. So if you add one more character, you will still have enough characters that you had before, right? And if you add one more character, that you still have all the character that you need for word 2 as well. So do you really need to iterate over every R here? The answer is no. You just need to figure out what is the first R which is sufficient to form every character that is there in word 2. And once you figure out the first R, you can simply add n minus r to your answer, because after this r, every position will be valid, right? So you will simply add n minus r to your answer once you figure out this r. Now, figuring out this r also is not straightforward. Basically, what you did is, instead of going from L to N, you, as soon as you find one sufficient, you increment your answer by n minus r instead, right? And you simply break out from this entire loop, because you have everything afterwards will be valid. So you simply add the contribution of everything and simply break out from the loop. But even now, this entire thing can go worst case order n square, right? So you need to figure out this r efficiently. It should not be the case that you try out this first, is it valid, then this, is it valid, then this, is it valid, and so on and so forth until it becomes valid. You can't do that. So what's the easiest way to figure out r in less than order n time? The answer is binary search. Notice that this entire thing is a step function, right? What that means is, if a particular point is valid, everything after that will be valid as well, right? So you can simply apply binary search to figure out this inflection point, or the point where it becomes valid. And if you do that, this linear search would be replaced with a binary search, and this entire thing would be replaced with a log n factor here. So overall complexity would simply be order n log n multiplied by c. Now, why c is something I would encourage you to pause and try to think by yourself. But the main idea is, instead of doing a linear search for r, we will do a binary search for r, right? Now, if you do a binary search, just to recap that part, you have some r with you, right? Now, in binary search, what you do, you will try to figure out the middle position, or in other words, you will try out this r first, and you will see, okay, is this valid, or is this substring valid? If it is valid, then I know everything afterward is valid, so I will try to search in the left. In other words, I found a point where everything is valid, so there might be a point before this that can be valid, which I am interested in. So I will search in the left part and completely skip the right part. If this string is not valid, it means there is no point trying out anything in the left, because if this entire thing is not valid, if you remove one character, no matter what you do, this substring will also not be a valid one, right? So you will simply skip going over the left and only search in the right part. So basically, at every iteration, you are bringing your search space to half, and overall in log n iterations, you will be able to reach your destination. Now, for every iteration, what you need, whether this L2R is valid or not, right? And how to compute whether this L2R is valid or not. The way we are computing that was, we try out, or we find out the frequency of every character between L and R. And once we have a frequency of every character, we compare the frequency with the frequency of words too, right? Now, if you do this, you will need order n time to just find out frequency, and then order c time to actually compare as well. So even though you need log n iterations, but in each iteration you will be doing this much operation. So overall, you would be doing these many operation, log n multiplied by n plus c, to just figure out r. And once you have r, you will increment n minus r to your answer, and you will do it for every possible L. So overall complexity would be n log n multiplied by n plus c, which is even worse than n square c, right? So obviously you can't afford this n here for sure. Basically what you want the sum of or the frequency of every character between L and R without actually iterating between L and R. So what's the best way to do this? Would encourage you to pause and try to think for a moment. The best way is you can use a prefix sum. What you want, you have total 26 characters, right? For each character you can maintain a prefix sum, and for each character you can figure out how many characters are there between L and R. That can be simply answered with a prefix sum. So we'll do a dry run in a while, but with the prefix sum you can simply replace this n with a order C operation. Basically you will go over the prefix sum of every character, and for every character you will simply do prefix of R minus prefix of L minus 1, and you will get how many characters are there in between L and R for every character that you have. So overall complexity would be order C plus 3, which is 2C. So this entire thing would then become order C, and the complexity would become order NC log n, which is much better than n square C for sure, right? So this may or may not pass the second problem that we have. We'll come to that, but let's first do a dry run and look at the pseudo code. So as we discussed, what we want is, given a L and a R, we need to find out how many characters are there between L and R or what is the frequency of every character between L and R, right? Now for simplicity we have assumed there are just two characters A and B in the entire string, but in the original problem you can have any lowercase English character. So you will maintain, instead of maintaining this 2 array, you will maintain 26 different arrays, one for each character that you have, right? So how to build this array? Simple, prefix sum. So let's focus on A first, right? For A, wherever you have A, you will increment your counter there. So you found one A, you will increment your counter here. Now is it an A? No. So you will not increment your counter, and this will remain same. What that mean? This means that until this position there is just one A, which is true, right? Now you got to this, you got A, so you will increment your counter, which again means until this position there are two A's that are there. You got one more A, increment your counter. You got B, which is not A, so you will not increment your counter, and this will remain 3. Again B, don't increment, this will remain 3. Again B, don't increment, remain 3. Again, what does it mean? This means that until this position there are 3 A's in total, which is true, right? And finally you got one more A, and you will increment your counter. The same you will do for B as well, but this time you will increment only when you look when you see B. So is this B? No, it will not increment. Is this B? Yes. So you will increment your counter to from 0 to 1, and so on and so forth. So every position here tells you how many B's are there in this prefix of the original string, and this tells you how many A's are there in this prefix of the original string. Now if you want how many A are there in this, what you can do, you can simply look at how many A's are there in this entire thing, how many A's are there in this entire thing, subtract those, and you will get how many A's are there in this entire thing, right? So same you will do for B as well. So now if you want to figure out how many A's and B's are there in this L and R, you can look at this one and you can look at this one, subtract these two, you will get 2. So there are 2 A's in between this L and R. Look at this one, look at this one, subtract them, and you'll get 3. So there are 3 B's in between L and R. So instead of iterating over everything between L and R, what you're doing now is you are simply iterating over every character. For every character you are simply doing or subtracting 2 numbers to get your final value, right? So to get this array or the frequency of every character between L and R, you now just need order C time. But this, or to get to this order C time, you need to build this array, and the part you build this array will take order n into C time. Why? Because you are iterating over the entire array for every character at least once, right? So building this entire array would take order n into C time, and order n into c space as well, because you are storing this entire array, right? So overall, this is how you will calculate the frequency of every character in just order c time. And rest of the things we have discussed already. So you will simply do, you will start with every position, every starting position L. For each starting position, you will try to find out the R by doing a binary search over R. While doing binary search, you will need the frequency of everything between L and R, or some L and some R. And for that, you can use this algorithm that we have discussed to get it in just order C time. Once you get whether this L and R is valid or not in just order C time, you can decide whether to go left or right. And this point will, or you will have at most log n of such points, because at every iteration you are dividing your array into half. So in at most log n iteration, in other words, in at most log n decisions, you will be able to reach your point. So overall, you will require order C into log n time to reach your final R. So let's look at the pseudocode as well. The pseudocode would be very similar, just that we will not do a linear search and do a binary search. So we'll start with every possible L. For every possible L, we'll target what is the first R that is there. Once we get this, we'll simply increment our answer with n minus R. Now, how does binary search function look like? It will simply be a binary search function. We'll take in a starting position start, which simply says where my array or sub array is starting from, right? So let's call this this particular function, this particular position. Now for this L, you want to find out what is the nearest R that satisfies the condition. So what you will do, you will start a binary search starting at this L. So let's call it L dash, and R dash would simply be the last position, because your R can anywhere between this and this, right? Now you will do a binary search between L dash and R dash. You will first go to some M, figure out whether L to M is valid or not. Notice that you will not search for L dash to M dash, because L dash can change in between. So you will search whether L to M is valid or not. And for that, you can simply use this algorithm to get this answer in just order C time. Once you get this answer, you will either go in the left or in the right. For example, let's assume that this is returning you false, that is L to M is not valid. Then there's no point searching in this part at all. So you will simply replace this part, and you will simply make your new L dash as this one and only search in this part. Now again, you will come to some M. For this M, again, you will not search between L dash and M, rather you will say whether L to M is valid or not, right? If it is valid, you will go and search in the left, otherwise go and search in the right, and so on and so forth. So that's what we're doing. We will simply keep on finding the mid and understanding whether start to M, not L to M, right? Start to M is valid or not. If it is valid, we will look in the left, otherwise we'll look in the right, right? There's a plus minus 1 difference here, which you can figure out yourself. So overall complexity, as we discussed, is now order n multiplied by the complexity of doing binary search, which if you look at, you are doing this while loop will take log n time, and inside this you have order C operation. So overall order C log n is the complexity of binary search. Now if you haven't reached till this point during the contest, would strongly encourage you to pause and try to code this solution by yourself. This may or may not pass for the second problem, for the third problem. So you need to optimize this further, but you should at least try coding this out, because that will help you understand and retain this concept for longer. So next, we need to optimize this as well. Now, which of these factors you can optimize? Firstly, you are this n is required. You are iterating over every starting position. This n is required. So let's see if we can somehow reduce the complexity of this function itself. So in this function, there are two parts. One, you are doing a binary search, that the outer for loop, and then you are for each iteration, you are finding out whether it is valid or not. Now, obviously, you can't do better than order C here, right? To do better than order C, you need, like, you somehow need to find out whether you have sufficient character or not without actually iterating over every character, which is very hard. So this is hard to remove. What that in turn means, you have to skip binary search as well and somehow still be able to figure out the exact same thing without binary search. Is it possible? In this scenario, yes, it is possible. Why? Because of the property of the function. So the function that we are after is whether L to R is valid or not, right? Now, let's assume that you started with this L. For this L, you found out this R is the one. This is the first R where everything goes good, right? So for L equals to 0, you found out that this is your R. And this you do by any method, doesn't matter, right? So once you figure out this R, now you increment your L. Now your L is this. What you are doing today is you are kind of discarding whatever R you had before and again searching for R in the new constraint wherein the string is starting from this P. Is there a way wherein you can reuse whatever you have computed before and still be able to like you can reuse that part and still figure out this R without resetting anything? And the answer in this case is yes. Why? Because let's say you for this L you got this R. What that means is if you start from here, this is the first place where every character that you need in words to exist. Now when you increment your L, will your new R be ever less than the previous R? Answer is no. Our new R would be strictly increasing, or rather increasing, because if it has to be a previous one, what that would mean is for a new L, you are able to get every character between this range itself. And this all characters were present in this part as well, which in turn means that in just this much characters you will get everything what you need. But that is contradiction because you said in the first place that this is the first character where you will have everything what you need, right? So what that means is our R is strictly increasing. So when you increment your L, either your R will stay the same or your R will increase. And once you pick or start increasing R, this R will never come back, and hence you can simply apply 2 pointers to figure out the best R for a L without doing a binary search. Okay, so the next approach is we will remove this log n because we know that in this particular scenario R follows a increasing path for increasing L, right? If that would not have been the case, you will not be able to remove this binary search at all. But in this scenario, it is true, and hence we can remove the binary search as well. So what we will do, we will start with this L, right? And we will start with this R here, and we'll see whether this L to this R is valid or not. If it is not, I will increment my R. Whether this L to this R is valid or not. If it is not, I will increment, and so on and so forth until I reach a point where this L to this R is a valid substring. Now once I reach this point, I will simply increment my answer to n minus r, right? Now I will increment my r, sorry, L. Now once I increment my L, I will check whether this is a valid one or not. If it is, I found my r and I will simply increment my answer with n minus r. Otherwise, I will increment my r and then increment the answer based on whether it is valid or not. So in this scenario, we wanted BB, right? So in this particular scenario, we have BB with us. So this is a valid one. We'll simply increment our answer with n minus r again. Now we increment the L again. This time, if you look at whether this is valid or not, this will not be valid because there are no, there's no 2Bs. So we'll increment your R. Now we will again check whether this is valid or not. In this case, it is valid. So you will increment your answer by again n minus r, where this is your new r. Again, increment your L. For this L, this r will still remain the same. Again increment, again, and so on and so forth. So basically, that's how you will proceed with the algorithm. So what will be the time complexity for each L? What you are doing, you are checking whether the current L2R is valid or not. Now, for this valid or not, we have seen that we can simply figure out in just order C time by using this prefix sum trick. So in just order C time, you can figure out whether this L2R is valid or not. If it is not valid, you will simply keep on incrementing your R. Now, for each R you increment, you will again incur a order C cost. Now, overall, you can increment your R n number of times. So overall cost would be order n into C. For a single, for all possible R. Now, in the same fashion, for all possible L as well, you will incur one order C cost in worst case. So you will simply add plus order NC. So let's look at pseudocode. The pseudocode would make this part a bit more clear. So the pseudocode would look something like this. What we are doing, we are trying out every possible L. For each possible L, we are starting with some R, and we are trying to increment our R to a position where it becomes valid, right? So we will simply keep on incrementing the R. For each R, notice that you are calling some is sufficient function, which will simply iterate over everything between, or every character in this F array and frequency of words to array, and compare it and return true or false, whether this is sufficient or not. So this will take order C time, right? Now once you figure out the best R that you have, you can again check whether you actually reached a point where you have best R, or it is not at all that point. This part you can remove as well. I would leave that as an exercise, why we don't need to check this. You can think about it and we can discuss in the comment section below, but this part you can skip checking fully. So what you are doing in total, for each L, you are first checking whether you have a valid previous R or not. So that will take you order n into C time, right? Now, whenever you are incrementing, you are again checking once. So that will take you order n into C time as well, because in worst case, you will be able to increment only n number of times. So overall complexity is now simply order n into C instead of order n log n C, which is much better than the n log n C algorithm, and will pass the second problem for sure. Will pass the third problem for sure. So this is the right time to pause and try to code this two-pointer approach as well. So I will not be showing you the code for this, because the code would be exactly what the pseudo code you see here. You just need to write the is sufficient function accordingly. So next we will be trying to optimize this as well.